Hello, everyone. First of all, I want to say thank you for coming to my session, or as Andy would call it, my show. He likes to refer to things that way. For those of you I haven't met, my name is Ginger Gilsdorf. I am a software engineer, a software person at heart, working at a hardware company, which actually is as cool as it sounds. As much as I love software development, algorithms, things like that, it's so much cooler when you have software that knows what the hardware is doing underneath and is optimized for that. So from my perspective, I get the best of both worlds. And I'm lucky that in my day job, I get to work with companies like Aerospike, see their software, optimize it for hardware, and just see the really awesome things that happen when we work together. And then on the same hand, I can go back to the Intel architects and say, hey, here's what the software developers are asking for. Can you do that? So from my perspective, I have a pretty great job. And in this talk, I really wanted to cover a lot about Intel Optane DC persistent memory, which I'm sure you've heard the name many times, especially in the recent future. And I'll go over a lot of the hows, the whys, the whats of that. And then I'm sure a lot of you are dying to get to the now what part. Okay, the hardware is actually out on the market. Now what can I do with it? Just so you know, at the very end of this, I will be taking Q&A, and Brian and Andy from Aerospike will be joining me, so you'll be able to ask pretty much any of the questions that you've been dying to ask. But if during the course of things I throw out an acronym that's not familiar, please feel free to let me know to go over that. All right, so I have my colleague Fal to thank for reminding me that I need to set the stage. How did we get to where we are today, and why are we here? So it kind of forced me to step back and actually consider that. And when it comes down to it, on a day-to-day basis, we make decisions such as these. This also allowed me to slide in a photo of my dog. But we do. We say, I love that sports car. It's fast. It's everything that I like. But when it comes down to it, am I going to pay the price for that? So compromising or settling, love my dog, would never compromise or settle for a goldfish, but we make choices like that. Had my cheesecake at lunch. But the point, of course, that I'm trying to get back to is that as software developers, in some sense, I think we've been settling. For many years, we really only had the choice. I want a data structure. Do I put it in memory? Do I put it in storage? It's really only been the two choices there. And then as software developers, we're very creative about how we work with that. I know that if I put something in memory because it's fast, I can also back it up to storage to persist it. But it's not, when you really think about it, it's not the most ideal situation. And of course, with storage, we do have a lot more options out there. Now that we've got NVMe SSDs, all the way down to hard drives. But in some sense, it is almost as if we're still looking at the Mazda line of cars instead of the Lamborghinis. I'm not a car person, so I don't even, not even sure what that is. But that's kind of the perspective that I think that we've been taking as software developers. And we're here today because there is something in the middle. I realize the flaw in my slide, though. I'm suggesting there's a better middle opportunity, but the same is not true for my dog. I have to point that out. So at Intel, we really like to confuse you with terminology, so stay with me. I'm going to do my best to clear the muddy waters. The Intel Optane technology umbrella covers these four areas here, and most of you are probably familiar with the term 3D crosspoint. That is the underlying memory media that was developed by Intel and Micron together. It's 3D in the sense that those memory cells are stacked, allowing us to pack many more memory cells on a device. And it's a really unique technology in itself that Intel's not publishing a lot of the details behind the technology, but it's a brand new form of technology. It's not transistor-based. So Micron has taken that media and done their own thing with it. Intel's taken that media added intelligence to the memory and storage controllers, the interconnect, some software. And all of that together we're calling Intel Optane technology. Now to confuse you even further, we have different form factors. So the one that's really the star of the show today is what you've heard referenced several times, Intel Optane DC persistent memory. This is the form factor that comes in a DIMM module. It literally slides into the slots right next to your traditional DRAM. This is the newest technology, the newest form factor out there. You've heard PMEM referenced several times. That's what we're talking about. You'll see the term non-volatile memory or NVDIMM. Those are all referring to this, either Intel's technology or another technology that's also non-volatile. And then we'll throw in there DCPMM, referring to the actual memory modules. This technology just launched last month with the Intel Cascade Lake second generation Xeon scalable processors. And this, in my humble opinion, is the most innovative way to use the underlying media. And it's really kind of the pinnacle of what this has all led to. But being Intel, we're going to confuse you a little bit. So we have the Intel Optane DC SSDs. Those have been out on the market a couple years. Those are for server products. But you also have Optane SSDs for client. And then, of course, we've got to make it even more confusing. Intel Optane Memory. This is built on memory drive technology. And this is not one that I've done a lot of work with, but it can essentially be used in your client systems to extend your RAM. But just so everyone's on the same page, when I talk about Optane or persistent memory, this is what I'm referring to on the left. Okay. And as I was talking about, different compromises that we make when we're developing software, this is what we're used to. Like we said, we have DRAM. It's fast. The latencies are in the nanoseconds. It's really, in terms of speed, that's where you want your data to reside. However, we also know that it's very expensive, dollars or more per gigabyte, and it comes in smaller capacities. So there's plenty of use cases where you just simply don't have enough DRAM to store a data set that you're looking for. Our storage tier has gotten much more diverse over the years, starting down with hard disk drives, tape, very, very affordable, but who's going to sacrifice that much time in their application? And then, all the way up to the Intel Optane DC SSDs. Again, they're a great choice for storage, but there's still this large gap in terms of speed, in terms of capacity, and in terms of performance. So what we've done with Optane DC persistent memory is bridge the two. If I had my way, I'd actually push this persistent memory tier much closer to memory and move the storage tier even farther down. And this persistent memory has DRAM attributes in the sense that the latencies are very, very close to DRAM. Again, with DRAM, we're talking in the 90 nanosecond range. Persistent memory, we're still in the nanoseconds, hundreds at the most. Compare that to even the fastest SSD out there, you're looking at milliseconds or microseconds if you're lucky. So again, in some sense, there is a little bit more of a gap between the two. But it's not just large memory. It's the fact that this media is persistent, and that's where you get the SSD attributes. So we're getting DRAM-like performance, but it's persistent. So this, as a software developer, this is a new way to think, a new way to handle your data. You've been asking for years, I want my data fast, but I also want to trust that it's still going to be there when I reboot. This is what this memory is intended to do. Just a couple of the details. All of this is public knowledge since the release. But this will work with your Cascade Lake CPUs. Each CPU has 2 memory controllers. The way to populate your system with respect to Optane DC persistent memory, the most you can have is a 1-to-1. So if you have one Optane DC persistent memory module, you have a DRAM module next to it. Since the capacities of each individual DIMM are 128, 256, or 512 gigabytes, at 6 channels per CPU, 2 DIMMs per channel. Put it like I mentioned, putting one Optane DC persistent memory in each channel, you can fit 3 terabytes of persistent memory on a socket. And that's not even including the DRAM that sits adjacent to it. So on a 2-socket server, which is fairly standard today, you're looking at 6 terabytes of Optane DC persistent memory. For a lot of people, that's pretty astounding. Just a quick thing about the speeds. We're running at DRAM speed, 2666 megatransfers per second. Again, the 2 types of media DRAM and the Optane DC persistent memory are physically and electrically compatible. They literally snap right in next to each other. And then the last point on there is that unlike storage, you're actually getting cache line size access to this media. You might have heard the term byte addressable. That's where this is coming. And I have a little bit more detail on why that's such a big deal later, but I'm sure those of you who are used to working in 4K blocks from storage, I'm sure you can appreciate what that does for you. Okay. So with this technology in DIMM form factor, Intel's enabled 2 main operating modes. And I'm starting with the one that I consider the least interesting, and it's called memory mode. I think Srini referenced this yesterday when he said there's plenty of companies out there using this persistent memory as a large cache. This is what he's referring to. The picture's a little bit misleading in that your application really is only seeing the persistent memory as memory. So your operating system thinks it has a terabyte of RAM to work with. In reality, what's happening underneath that is that as data is being loaded into RAM, it's going through the persistent memory layer and being cached in DRAM, and then going up through the CPU caches from there. So there's plenty of applications that can take advantage of something like this, where perhaps you have a working set close to your DRAM level, but you want a level of memory close to that so that you don't have to swap out to disk if you run out of space for your working set. So this is completely transparent to the operating system or the application. It's basically plug and play. I can put a lot more memory on a system and go wild. A lot of people doing this, but this is not taking advantage of the persistent nature of the media. So even if you're treating this as volatile, the media itself is persistent. So we enable this volatile mode by holding onto an encryption key, and then at the end, just discarding that. So if you are working with data that's not meant to be accessed later and you do not want it to be persistent, you can rest assured that no one will be able to access it. But again, it's not nearly as interesting as the next mode, and which is also the one that Aerospike has recognized the value of, and they've done the software work that it takes to work in what's called app direct mode. So in this case, your operating system actually sees 2 separate pools of memory. So I still have my regular DRAM. I can allocate to that, just call a malloc, and I've got my regular DRAM that I'm used to working with. I also have a pool of persistent memory. So as a developer, this allows you to determine there might still be some data structures that are better to reside in DRAM, where there's some that are a little bit less latency sensitive, but will really benefit from persistence. So you have a lot more flexibility in where you place your data. Again, the really important thing is that while the media is persistent, it's at a near DRAM-like latency. So you can, in a lot of senses, treat it as DRAM that persists. It does require software modifications. You have to tell your software specifically, I want memory from the persistent memory region. And there's a few other nuances that go along with that as a programmer, but it's not that difficult to do. And with that, you get the benefit of persistence, which in many cases is much more valuable than just having a large pool of memory. A quick note on that yellow box. There's one more mode that is somewhat interesting in that it's called storage over app direct. This one allows you to plug in your device, treat it as a block device, access it like you would it was an SSD. That it works in some use cases, but again, app direct mode has some advantages that we'll go over. So I think that it really is kind of the shining example of this technology. Okay. So we come to Aerospike, and in my role, I was really lucky that Aerospike jumped on this immediately. In a lot of ways, it feels like Aerospike was designed around app direct mode, and app direct mode was designed around Aerospike. They really do work really nicely together. So you should be familiar with kind of the general operation of Aerospike. Your client knows which data node to go to access data. The data goes to the index to find the location, points to the data, and retrieves the data. You can see the index is referenced every single time. It's a really important data structure. Aerospike's original implementation was to put that in DRAM for speed. It makes a lot of sense. Now that we have persistent memory, let's put the index in persistent memory. How many of you hate restarting Aerospike or restarting a server because of those the indices? They can take a very, very long time to rebuild because they have resided in DRAM. If you need to do, I think Srini was talking about, or someone was talking about having customers hold on to Aerospike for years because they didn't want to go through the pain of upgrading, knowing that shutting down their systems, it could take a couple hours at a time to get one system up and running. So let's put that index in persistent memory. Let your data reside in storage, however you choose to do that. You still have DRAM. Totally up to you what you do with that. Again, this particular use case is really showing the benefits of both Aerospike and of Intel Optane DC persistent memory. Okay. Just a little bit on the programming model that enabled this. If anyone's familiar with SNIA, or the Storage Networking Industry Association, it is an industry-wide association. It's not an Intel-specific thing. There's many partners across the industry that contribute to this. They together have developed the standards that meet this NVM programming model. And this is a little bit confusing, but you can see from an application point of view, there's several ways to get to the persistent memory device. The one that's the most interesting that we've been talking about involves the persistent memory aware file system, and that manages your access to the device. With that, you use the kernel to memory map this map the persistent memory into your address space. And this is on the right side of the screen. What this allows you to do is to pull information or data directly from your PMEM device into your CPU caches. You're not going through the kernel. You're not doing the I/O stack. You're not going through DRAM. So this is much more flexible than bringing traditional storage into memory. And at the level of cache granularity, there's a lot that you can do with that. It's a very, very powerful model. Intel's contributed to what we call the Persistent Memory Development Kit, Vmdk. It's a kit in that it's a set of software libraries that allow you to access the persistent memory devices in a number of different ways. And Aerospike was able to use one of the libraries to build their software that supports persistent memory. Okay, and then from here I wanted to show if you are already an Aerospike user and you're thinking this sounds crazy to configure, I don't know what to do. I'm going to show you it's actually very, very simple. I'm assuming in this picture a 2-socket system. Not the only way to go, but this is just a way a lot of people do, in that each socket has access to persistent memory and DRAM. They actually are separate regions in the in the system. So you do have to treat them as separate regions. So the first thing that you do is just provision them and say, I want to use this media in app direct mode instead of memory mode. There are some utilities out there that are being integrated with Linux. They're fairly easy to use. Again, each CPU, the memory attached to each CPU is a separate region. You're not going to see the entire persistent memory region in one namespace. Aerospike luckily has this auto pin NUMA setting. If you haven't used it, you'll want to start using it with this memory. And what that does is allows you to run 2 instances of Aerospike, each one using the local CPU, local memory, local persistent memory, networking as much specificity as you can per NUMA node. When you mount a file system on each of those namespaces per CPU, this gives you a device to work with. All you have to do is mount a file system with DAX, direct access. ext4 is shown here, but there's also other options like XFS. Once you mount that, you've got a mount point to work from. There's really 1 or 2 lines that you need to add into your configuration file. Tell it, I want my index in persistent memory. Here's my mount point for instance 0. Here's my mount point for instance 1. Aerospike does the work underneath to determine which memory maps to which instance. So really, truthfully, that's as simple as it is to get started. Now there's some work being done in the background that you as an end user don't really need to worry about. Aerospike, once you've set it up this way, will just run as usual. When you're ready to shut down, you shut down as usual. Nothing to change there. But what happens when you're shutting down is that Aerospike is ensuring that any data that's been in the caches and has not made it to persistence is flushed. So if there's anything that Aerospike's brought into the caches and has not been evicted by normal operation, there's instructions that go in there and explicitly say, make sure that this data gets down at least to the memory controller. At that point, it's considered power failure safe. And then once you reboot your system, that data is still there. If you were to crash unexpectedly, there's the possibility that some of your data would be in the cache and would be lost. But Aerospike builds around that because this is your index. You can always go back and rebuild the index if you need to. Instead of doing this operation every time you write to the index, we're doing it on shutdown. So you're still retaining a lot of that performance. As far as value prop or the ways that the users will benefit from this, firstly is lower cost. There's 2 ways to think about this. On the left here is a system that I've actually run some performance data on. The system on the left with DRAM had 1.5 terabytes of memory of DRAM. Same storage underlying. The system on the right, I had 1.5 terabytes of persistent memory. DRAM to spare. Those two systems, if you were to configure them and purchase them, the one with persistent memory is cheaper. And again, like I said, you have that DRAM to spare. So from a system-to-system cost, if you're outfitting it in this kind of manner, you're going to save money even without changing your structure. In case number 2 is probably where a lot of you will end up. Knowing that the index capacity often limits the number of records you can store per node, think what you can do if you have up to 6 terabytes for your index. I know with SSDs, there's tons of SSDs with great capacity. If you have SSD capacity to spare, but you don't have room for your index, now you do. So there's some discussions going on. Can I take my 20 node cluster down to 5? Very possibly, very possibly. That's harder for us at Intel to test. So we're really curious to see how that works out in implementation. But the possibilities really are there that you can do some serious node consolidation. Faster restarts. This is the value prop that really takes advantage of persistence. With DCPMM or Intel Optane DC persistent memory, when you restart your computer, your server, the only thing Aerospike has to do is go through and reattach to the existing index. It's still there. It's as simple as updating a few pointers. And then your index is there, you're ready to go. As most of you know with DRAM, that's not the truth. The index is gone, and you have to scan through every single record on SSD to rebuild the index. For the same system I showed before, with a terabyte of index and 8.7 terabytes of data, the DCPMM systems was up and running in 35 seconds. That's not including the full reboot time, but once I started Aerospike, it was up and running in 35 seconds, ready to start taking queries. The DRAM system took 4,745 seconds. I think it was on the order of 35 minutes. I mean, the sheer scale there, 135x faster, is something that is a real benefit. So again, if you're looking at doing upgrades for an entire cluster of servers, this is monumentally important to your ops team. In terms of performance, we've been saying DRAM-like performance. What does that actually mean? In the testing that I did with Aerospike, with that data set that I showed you earlier, the system with persistent memory performed at 95%, that of the one with DRAM. And there were some constraints in there that in many cases, you're not even going to see that 5% hit. It is heavily workload dependent. What your mix of reads and writes are can affect this. But in the testing that I've done, the testing that Aerospike's done, there's a lot of use cases where performance is nearly the same, imperceptible difference. So again, this is just one workload that I ran, 95% performance. Again, in many cases, you're not even going to see that at all. I will leave this up here long enough if you want to take snapshots, but this is the now what section. The first thing that I would do is start with Aerospike's Enterprise Edition support team. They are well versed in this technology and how to support it. They can help you make decisions of when you're ready to implement. The second thing you'll need to consider is your OEM or your CSP. Luckily, we have one of the OEMs here today, so you can feel free to ask her. But they're at different stages in the availability zones. So just check with them and see when they're ready to support you. As far as the operating system goes, I've tested this on 3 of the major Linux distros just fine. The kernel, it's important to note that the more recent your kernel is, the better your performance will be. I'm working on primarily 4.18 and above. I think if you're at 4.4 and above, you're fine, but I would stick with something as recent as possible. There's a great quick start guide on Intel's site. The Intel Developer Zone has a lot of resources and tools to check out. And then this persistent memory, pmem.io. This captures a lot of the work that's gone along, and it also links you to the Vmdk, the development libraries. With that, I'm going to bring up two of the other stars of the show. That's here. And we will take Q&A jointly. Oh.
I think that's my cue.
Yeah, I think, and I'll give you a second if you want to, just give a minute or two's perspective on your work. Go for it.
These are pictures. Am I wrong? Oh. What do we want us to say?
If you just want to give maybe a minute or two of your perspective of the joint work we've done, or where you think
sure.
we're coming.
So, perspective on Intel persistent memory. It's been a really interesting journey since, what was it, like 3 years ago?
It's been 3 years ago? Yes, I believe 3.
And so, what I usually say about persistent memory, I say a couple things about it. First of all, there's only been a few methods to storing bits in computers since the beginning of computers. And that's, you burn a hole in something, that's one way. Or sorry, you punch a hole in something, you make a hole, right? And that covers paper tape, punch cards, but also CD-ROMs, right? They got little holes in there. The second thing is you make a little pool of magnetic flux, and then you magnetize it, and then you've got a bit there, you can go read it again. And the third way has been create a little circuit and charge it up. That is the only way we have ever stored bits in the history of computer science. There's now a fourth way. And the general idea of, I don't know if you're calling it phase change memory, it's not been called, yeah, she's not allowed to call it phase change memory. Go look at the Wikipedia page. But basically you take a little piece of a substance, you melt it, and then when you cool it, if it cools slowly, it forms an amorphous solid, and slowly it's a crystal, and fast it's an amorphous solid. And those two have two different resistive properties, and then you can just go read the resistance. That is the general concept. Now, whether it's really a crystal or not, Intel's not saying, is it, it's not really a glass. Glass behaves that way. But this idea that you have a substance that you can then, melt and reform and then read the resistance on, people have postulated it for decades. HP was well known for taking a run at the problem, and Intel finally did it. And the characteristics you saw in here, I thought were really exciting. I was sitting there in like 2011 going, look, if NAND keeps going like it is, and we need about 2 to 4% RAM to NAND ratio, once we get up in the area of 100 tera NAND servers, which we now have, right? 6 terabyte drives, and you stack up 10 of them, 12 of them, and they're at 6.8, you're at about 100. Okay, so geez, we're going to need 4 tera of DRAM. That's going to be aggressive, and DRAM isn't improving, et cetera, et cetera. So I was considering whether to ask Andy and team to embark upon some new indexing strategies, or whether, or what we were going to do. And then Intel showed up with persistent memory. And so, it does exactly what we needed, right? So if you look at that percentage, being able to put 6 tera of this stuff alongside 100 tera of NAND for your index is just right. So it really fills the hole for that. And I've been saying that I hope this stuff has the level of applicability, because why wouldn't you use it? Right? You saw the performance numbers, they're pretty much the same. There's in the high write cases, yeah, you lose 5% or something like that. And it's cheaper and bigger. Why wouldn't you use it? When we've talked to some folks, they say, well, so I can start using small objects again, right? I don't have to use big objects to try to save on DRAM. So I've been a strong supporter of the technology. I like the reliability of it, and I think it's pretty cool. So I know there's a lot of naysayers out there. Some of that was based on the fact the early packaging of Optane in the NVMe form factor, which also actually has more benefits than I think was ever due. But this was always, the goal was to get it on the memory bus where it shined. So that's my perspective on it.
Okay, what do I have to add? Yeah, let me start with the thing I usually say, the summary about this memory, in particular for Aerospike indexes in it, is quite honestly, if it's available to you, there is really no good reason to run Aerospike's indexes in RAM anymore. I'll qualify that 5% difference Ginger showed. She's pathologically honest in her benchmarking and picked the worst case for PMEM, pretty much straight up and down. And Brian mentioned write loads. I'm going to qualify that. Really, the only place you can see a discernible difference between a PMEM index and a RAM index is not in a write load, but specifically a pure insertion load. The reason for that is after the fact turned out to be obvious, but our index is a binary tree, an RB tree. If you just do a write, that's an overwrite, you only affect one index element. You just change the metadata in the index element. If you do an insertion or a deletion, on average, it turns out you affect 4 for a red-black tree. So essentially, when you insert something, you're affecting 4 index elements instead of 1. So the actual PMEM flush load overall is a factor of 4 worse for insertion as opposed to overwrites. So yeah, really the only place that significant, and again, single % differences show up with RAM is in pure insertion loads. If you have a mixed write load, mixed read writes, or a lot of your writes are overwrites, as is usually the case with most, with a lot of use models, then there's pretty much no difference. So yeah, actually the performance is really closer, even closer to RAM than what Ginger is talking about. Ginger is also sort of worst case in that she only ever shows comparison of Aerospike index in PMEM to Aerospike index in RAM. But as of our 4.3 release last summer, we can also put the Aerospike index in SSDs. And we worked very hard on that to make that operate absolutely as close to the limits that device physics allow, and I think we did a fantastic job of that. But after all, the device physics underlying your data in SSDs are the physics of SSDs. And while the performance is actually probably much better than you think, if Ginger were to be fair to her own product and put all 3 things up, in reality, although PMEM is somewhere in the middle logarithmically in terms of hopefully price, but size and latency, in practical terms for Aerospike performance, it's really jammed up, indistinguishable to RAM, and very far away from SSD. And it's also just plain easier to configure for us than an index on SSD. We tried to make that as easy as possible, but there are some realities there that mean that you have to configure certain things carefully and accurately if you want to get the best performance. And with index and PMEM, you just don't have to worry about that. It's absolutely identical to what you would do with RAM. You just don't care. All you do is you add the few lines that she showed you where you just say index type PMEM and say what the mount is, and that's pretty much it. So yes, again, circle back to my original, if you have access to this stuff, there really isn't a good reason to use anything else, at least not RAM.
Yes. So I'm going to answer the first question, because I know what your first question is. Actually, it's the second question, because the first question you're going to ask is, where can I get this now? I'm not going to answer that. So the second question you're going to ask is, what does this do to a pure in-memory database like, say, Redis? Right? If I go up to the PMEM Google group, I'll see a bunch of people taking the open source Redis code and putting it on top of PMEM. Now, Ginger mentioned that people who are doing that are primarily doing that with the pure RAM mode, but that's not actually true, right? So they're actually using, some people are porting AppDirect, using AppDirect mode and putting it on top of both Mongo open source and the Redis open source edition. And I think what's interesting about what Aerospike has done coming out is to say, hey, look, so yeah, sure, that'll take your in-memory data set from 1 terabyte to 6 terabytes. And that's all well and good, right? You know, using this kind of tech to get a factor of 6 of scale, data scale, out of your in-memory databases like Redis, that's pretty cool. On the other hand, what we did was, when I was thinking about this, I said, well, that's fine, but I mean, Aerospike users they're not happy with 6 terabytes per server already, right? The level of scale that you guys are working with is already way past that. Our very first deployment in 2010 was at 2 terabytes per server, and nobody runs with 400 gig drives anymore. So I thought, well, yeah, sure, the RAM-based guys are going to get this 6x, but in my mind, who cares? We're interested in taking our 20 terabyte, our 10 terabyte servers and pushing them to 100 terabytes and getting that order of magnitude instead of going from 1 terabyte to 6 terabytes. But I will give, you should go out there to the Google group. I think there's some pretty interesting stuff, and Andy hangs out there, and the different people trying to do sort of pure in memory. That being said, of course, it would behoove Aerospike to eventually do the same thing, because there are some benefits, right? If you really do want to do RAM-based stuff, it would behoove Aerospike to do that. As an advisor to the company, I would advise them to do that. Because there are some benefits, right? Having that level of speed at, that extra 6x performance is really kind of an attractive thing. So hopefully we'll see that kind of technology from Aerospike in the future.
Yeah,
That was your second
I
question.
tried to summon it. It looks like a lightsaber, but it just doesn't come when I call. I went a couple of weeks ago to Intel's conference
Vmdk, right?
down at, what was it called again?
Oh, the Hayes Mansion.
Yeah, Haynes
in
Mansion
San
or
Jose,
something,
San
right.
Jose, yeah.
So it was all about PMEM, half about PMEM, which, that's a pretty good fraction for me. And so I had a couple days to think about it. And yes, of course, a lot of people are asking, or they even assume that, oh, you're using PMEM, that must mean that everything is in PMEM. And we've had a hard time sort of explaining, well, what we've launched so far, no, it's an index in PMEM, your data is still on SSD. And actually, that's a very practical combination. And really, I think in the end is the most practical combination at scale. But of course, people are asking about, what about the data too? Isn't that going to go into PMEM? And the answer is yes. But again, we don't want to do it like our competitors have, where it's just bigger, cheaper, but still effectively volatile RAM. We want to leverage the persistence, and we're going to do it right, or we're not going to do it at all. So we are planning to do this. There are a lot of options as to how we were going to go about doing it, and so for that reason, it was kind of good that I was at that Intel conference, because I had nothing to do but go through them all. And we now think we do know the best option, and we do know how we're going to do it. And I'll just throw in a couple of jokes I got from the Intel conference. Is what's worse than a memory leak? A persistent memory leak. And yes, in the Intel keynote, the speaker mentioned casually at the beginning, and this is, part of it is serious. It's true that this is so radically new, as Brian said, that we as programmers are kind of having a hard time getting our heads around it. Like, what, you don't really realize until you try to get your head around it how steeped we are in our habits for all our lives of knowing the way the world works is you have fast volatile storage and, slower block persistent storage. And now here's this thing that, like, whoa, how do I use that? And so far, as the Intel keynote speaker said, most of the usage has been unimaginative. It has been big, cheap RAM, and they're kind of disappointed that no one's really using the persistence well yet. But then he also said, well, we sort of get it because it's hard to get your head around, and so we're trying to build up libraries and toolkits around it to help you as developers leverage this. And then he said, it's kind of tough to just tell you guys, here's a pointer to 3 terabytes of PMEM, go have fun. But actually, that's exactly what we did with our index, right? Is we took a pointer to terabytes of PMEM and we went and had fun because we already had all the internal memory management and garbage collection or dealing with what the concept of a persistent memory leak would be. We had all of that figured out already. And so it was sort of like we were going sport fishing and a marlin just jumped into our boat when this stuff came along because we were actually well suited to going and having fun with 3 terabytes of memory. So that was true for the index. The index marlin jumped into the boat. The data is a somewhat tougher nut to crack because it's not this perfectly managed heap that we already had in place. And so we're, still orbiting exactly the strategy for doing it. But I can assure you now that I'm pretty sure we know how to do it, and we're going to do it right, and it should be spectacular performance. So for people who don't actually need more than 6 terabytes a node, we do hope to fill that cell in the table of all the combinations you can do for Aerospike index and data. It's kind of cool that they're independent, and you can pretty much mix and match them any way you want. I mean, yeah, of course there are some silly ones. Why would I have my data in RAM and my indexes on SSDs? But principally you could. So yeah, we're going to fill that bucket. What?
So just like
sure.
the Oscars were being played off stage.
Yes.
So by Q&A we mean come and see us later.
Oh, really?
So that the next
Can't have any live Q&A?
we're out of time.
Oh.
The next session is starting in 10 minutes. So.
That's what happens when you have 2 people that can't stop talking, right,
Answer
Brian?
one of your questions.
Thank you.
Thanks.